Hello, my name's Alistair. I work at Western Digital as part of the RISC-V software research team, and today I'm going to talk about porting TOC to OpenTitan. So today's talk is going to start off with first explaining what OpenTitan is. Then I'm going to talk about TOC, the TOC apps, and kind of explain the TOC ecosystem. Then I'm going to give the status of TOC on OpenTitan. And finally, I'm going to go into this deep dive of the USB CTAP support in TOC and OpenTitan. So this deep dive will be specific for this example, USB and CTAP, but it'll be a good kind of generic overview of how everything works together and how, if anyone's interested in contributing, they can kind of follow this. And it'll end within the demo as well. So first off, OpenTitan is an open source Silicon Root of Trust. It's backed by a large number of companies, including Western Digital, and includes a RISC-V processor. It includes this IBEX 32-bit RISC-V core. On top of that, around it, it applies a lot of different IP. So it has some crypto IP, things like AES and HMAC, as well as your standard IP, so GPIO, UART, and USB. It's designed to be a root of trust, so for example, in use in security keys or TPM-like things. And there's a large range of use cases that's being planned for it. So TOC. So TOC is an embedded operating system written in Rust. I sometimes see some misconceptions that it's an RTOS. It's not real time. There's plans on kind of addressing that, or discussions at least, but right now it's not. So here's a kind of what the overview looks like. Hopefully you can see my mouse on the right-hand side. I'll actually come back to this diagram later and talk about it in more details. But TOC kind of does a few different things. So it enforces security and isolation. It does this both inside the kernel, so down here, and above the kernel with these apps. So inside the kernel, we use Rust. So for anyone who isn't familiar with Rust, it's a generally safe language. You can't do kind of dangerous things such as accessing raw pointers or raw addresses and things like that. And it has this strict borrow checker that tries to avoid compile bugs. This sounds like a pain if you're kind of used to writing in C, but what it ends up being is basically enforcing all the rules you follow in C anyway, just having the compiler check them for you. But I mentioned you can't access raw addresses, so how can you do like MMIO accesses to read and write from a UART register, for example? So Rust knows it's a problem, and they have this unsafe keyword to allow you to do this. So the unsafe keyword basically tells the Rust compiler that you know something that it doesn't. So if you were just reading and writing to some address in memory, this is probably not a good idea. But the unsafe keyword kind of tells the compiler, look, trust me, I know what I'm doing here. It is okay. And in the case of reading and writing to UART, for example, that is okay. That is fine. So you can say unsafe, register, read from this register, which is the UART register, and the compiler will let you do that with this unsafe keyword. And so the way the TOC kernel works is you're only allowed to use this unsafe keyword down here in the drivers and up here in the kernel. So the drivers obviously need it to read and write directly from hardware. And the kernel, which is in charge of scheduling and syscalls and things like that, can use it as well for some complex, more complex operations. So the unsafe keyword doesn't mean your code is bad or wrong. It just means you're kind of doing something that might not be safe. And you are telling the compiler that it should trust you and you know what you're doing here. So these capsules, where a lot of the TOC functionality comes from, are not allowed to use the unsafe keyword. So because of this, we can limit a lot of the attack surface from these semi-trusted capsules that do run in the kernel space, but can't use these unsafe keywords. On top of that, then we have the syscall interface, and the apps run on top of that. So the apps can do anything they want. They're completely untrusted, and we use hardware to isolate them from each other in the kernel. And I'll talk about that in the next slide. So TOC apps can be written in C or Rust using libtoc-C or libtoc-RX. You can actually write them in any language as long as it runs in bare metal environment. But TOC has these libtoc libraries for Rust and C. So C apps probably have better support, but OpenTitan likes the Rust apps as they provide the same kind of Rust security that the kernel gets. And TOC uses in the ARM world the MPU and in RISC-V the PNP to enforce isolation between the kernel and the apps and apps and each other. TOC's always single-threaded, so there's only ever one app or the kernel running at a time, and we swap on and off the PNP to do this. This is the top logo, and this is a much simpler version of the previous diagram with OpenTitan hardware, the boot runs, then TOC runs, and then we have apps running on top of that. And so apps can only access their own memory or flash space. There are calls to, say, increase this if you need more, and there's IPC calls to do inter-process communication and things like that. But in general, they're only isolated to themselves. So the app interfaces the kernel. So the apps use system calls, or syscalls for short, to communicate with the kernel. So there's 4 main types. There's actually a 5th for memory operations, but I'm not going to go into that today. And the 4 types are listed here. So the idea is, in everything in TOC, everything is asynchronous. So all of these calls, except for yield, are asynchronous. So the app will first start off by running allow with a buffer. So for example, if you want to print, you'll hand the kernel a buffer with the allow command, with the whatever you want to print, the string. Then you'll subscribe a callback. So like I said, everything's asynchronous. So you want to know when this thing's finished. So you subscribe to a callback. Then you run your command. So your command can be read, write, or something like that. So you'll run in the UI example of printing. Let's say you'll say the print command. The print command will just return, but your data wouldn't have printed yet. So then you'll yield. Yield is then giving up control. Your app is basically going to sleep. And at this point, the kernel can schedule in other apps or something else. Or if there's no other apps, it'll just run inside the kernel. And then when your event occurs, so the print finishes, let's say, then your callback will be called. This is kind of what the data, the memory looks like inside TOC. If anyone's interested, I'm not going to talk about that today. I don't have time. I mentioned just quickly that the scheduler, app will yield. Your app doesn't have to yield. The TOC, interrupts. The TOC has a timer interrupt that will allow multiple apps to be scheduled if you don't yield. We don't rely on the app to behave and yield. So TOC on OpenTitan. So most of the work happens, pretty much all the work happens on mainline TOC. So you can see there's a list there of all the devices we support. I'm not going to read them all out to you. The main one that we're going to talk about next is the USB CTAP. And there's lots of upcoming work. So for example, we want to use ePMP, which is a RISC-V PMP enhancement coming out of the TE working group. And we can use that to even protect the kernel from itself in hardware, which will be interesting. There's 2 things related to storage. So we want a key value file system to store data persistently in Flash. And related to this, we want these storage ACLs, so access control lists. How do we say that app 1 can only read and write its own data, or app 2 has its other own data, maybe app 3 can read and write both, things like that. And syscall filtering. So I mentioned we don't really trust apps, but right now they can all access all the syscalls. So maybe we want to limit that. So maybe say, this app can only do I2C operations and nothing else. So more kind of security constraints on top of the apps. So that's it. There's lots more than that too. If anyone's interested in contributing anything, and come along and TOC's welcoming and send a PR or open an issue. So that's it for my quick kind of overview of TOC and OpenTitan. I'm now going to go into a specific example of the USB CTAP implementation, because I think it gives a good, like I mentioned earlier, I think it gives a good indication of how the whole process goes. So I'm going to first quickly cover what CTAP is. So it's the Client to Authenticator Protocol. It's developed by the FIDO Alliance. It's actually version 2 now, CTAP 2. And it's what's used to communicate between, say, your web browser and a security key, like a YubiKey. So when you go to log into a website and it asks for a second factor or even first factor, CTAP is the protocol between the web browser and the security key. It works over USB, Bluetooth, or NFC. In this case, we're just doing USB. And luckily for us, there is already a Rust crate, so you can see there, that implements it. So a Rust crate is kind of similar to a Python pip package, and we can just kind of install it through Cargo, the Rust build system, and use its features there. So that's really helpful. So I mentioned we come back to this diagram. So what's going on here is I'm going to talk about how to implement, or I implemented the USB CTAP support here. So first off, we'll start down the bottom. So we need USB support in hardware. So the low risk group have done that. They've added support to OpenTitan, so that's that. So then we need 2 things here. We need a peripheral driver and a hill. So the hill is a hardware interface layer. So these hills are Rust traits if you're not used to Rust, they're kind of like a C header file, let's say. And they describe all the functions that you have to implement to do this, both on the driver side and that someone can call to use this. And hills have to be hardware agnostic. So adding a hill can actually be quite a bit of work. I added one for the HMAC in OpenTitan, for example, and doing this in a way that suits all possible, we're trying to suit all possible use cases for all hardware, ends up being somewhat complex. And how do you report errors and things like that. In the case of USB, there was already one there. For a lot of the standard devices, there's already one there. And it just kind of depends. It's pretty easy to see if it's one or not. So in this case, there was, like I mentioned, there was a USB hill. So I just had to add the device driver, or the peripheral driver. So depending on the device, this can be a lot of work. USB is quite complex, so this was a lot of work. But you basically start with the hill and then implement the function. So there'll be a read or a write or something like that, and you kind of make each thing and handle interrupt, things like that. It's unlikely you're going to need a kernel change up here. That's only if you kind of were adding a new scheduler or something like that. So once you have your hill and the implementation, then there's up here. So now we need a capsule, a syscall interface, and an app. And so how you split this is kind of up to you. So in this case, we knew we needed a CTAP capsule, some sort of syscall, and implementation and user space. So TOC has a rule that no external dependencies, no external crates can be used inside the kernel because we can't trust that they don't use unsafe, basically is why. So in this case, it made sense to put the CTAP implementation, most of the CTAP implementation in the app. This has the other advantage of a CTAP implementation has to decode CBORD data, which is this binary data. It has to serialize and deserialize it. And these are common problems in security. It serializes and deserializes is overflows or some sort of bug in there. So moving this all up into the app user space, we can then isolate it to the app. So if there was a bug, someone could say take over the device with it. They would just be isolated to the app. They wouldn't be isolated to the kernel. So the IDO, so the implementation put all the work pretty much up here in the app. And we have a very small syscall interface, and we still have a CTAP capsule here in the capsules, but it basically just handles, passing some buffers around and doesn't really do too much. It kind of just handles raw data. It doesn't parse it or do anything with it. It does have to set up the USB endpoint. So when we plug a USB device in, then we advertise what we are and what we support. And so the CTAP device, or sorry, CTAP capsule handles telling the hill and the device driver down here, and then the USB hardware, the endpoints to advertise. But besides that, it just handles interrupts and moves data around. So the actual decoding and everything happens up here in user space, which is great. It means we can reuse existing crates, and it means we've isolated ourselves from a security perspective. So that's kind of it for my overview there. I'm now going to cut across to myself again, talking about it in a demo. So I have a demo of this running. So quickly, here's the Nexus board, the Nexus video board sitting on my desk. This is the UART and programming interface, the standard connections to the FPGA. And here's this special PMOD PCB designed for OpenTitan. So here's the GPIOs from the Nexus board. And this PMOD is used basically to shift the voltages and everything for USB. And this then plugs into my host, and that's the only cable actually required, besides power, the only cable required for the CTAP implementation once you've programmed the TOC binary onto the board. So that's it from me. I'll hand it over to myself again. So first up, I'm going to run LSUSB, so you can just see what's connected. And now I'm going to power up the Nexus board that we use as the OpenTitan development platform. LSUSB again, and you can see there's these two new ones that weren't there before. So that's the OpenTitan, the serial interface, and the programming interface. So over on the right-hand side, I'm going to attach to the serial interface. In fact, over here, I'm going to run make. So it's just make flash OpenTitan is the target. We're going to build this CTAP features example, and we're going to enable these custom features. So this is libtoc rs while it's building. libtoc rs, which is the TOC library for Rust, and it includes some examples in it. And this make command just calls cargo under the hood. So that's all done. It's not going to flash it, it just builds it. So now I'll go over here. So here we are in TOC. We're in the TOC boards OpenTitan directory. So this is where the OpenTitan specific stuff is. And we're going to run make here as well. So I'm going to run, so I'm specifying the OpenTitan tree. This points to the OpenTitan repo where we use the SPI flash binary from there. I'm pointing to app, which is then the app I just built. So it's in libtoc RS. It's the RISC-V 32 IMC app, which is the OpenTitan architecture, the OpenTitan board, the CTAP features app, and the TBF file. So the TBF file is basically a stripped out ELF with a different header, and that's what TOC uses for its apps. So I'm running make and flash app. So that's going to build the TOC kernel, build and bundle the app into the kernel, and now it's flashing it to the SPI. So this is, you can see here, we're downloading it, and here's the serial. This is the boot ROM printing as it processes each frame. So we'll just wait for this to complete. There we go. So this is the boot ROM saying bootstrap done. The boot ROM initialization is completed. We're jumping into Flash. So here, this is the first and only print from the TOC kernel. So the kernel says initialization complete. We're entering the main loop. And now we're starting the apps. So there's only one app in this case, and it's the CTAP app, which prints starting CTAP feature example, creating buffers, creating authenticator, and it registers its callback. So when I say the app's printing, it's not actually writing to the UART, it's doing syscalls into the kernel, and the kernel then prints it for the app. But all the statements and all the strings come from that app. So the app is now yielded. So basically what it's done is it has created a callback for when a CTAP event happens, and then it's yielded. So this app's no longer running. If we had other apps, they would be running as instead or as well, depending if there's more than one. But right now, this app's not running. It's waiting for a callback. So now I'm going to open up my website. So I'm going to log in. So I'm just logging in to Fastmail, which is the standard email provider. I'm actually going to take this off the screen because getting to the security settings shows my phone number. And I'm just back here. So I'm trying to set up two-step verification. So I'm going to my password and unlock that. So I'm going to set up two-step verification on my account. So I'm going to use the security key over here. Here we go. So this is Google Chrome saying, or Chromium, I guess, saying use the security key of Fastmail. And you can see there's lots of stuff going on over here. So I'll actually just wait for that to finish. There we go. So this is where we stopped last time with registering CTAP callback. So now the callback happened, and we've been doing communication with the host, negotiating CTAP things. Now we're creating a credential for Fastmail. We generate a key seed from a nonce, the app, and so this nonce is a number only used once. It should be generated from a random number source, a secure random numbers generator. At the moment, it's just statically hard-coded. We don't have a random number generator connected up in TOC and OpenTitan yet. So app is setting up a HMAC in the kernel and starting HMAC run and yielding. So what the app has done is it's calling into the OpenTitan hardware has a HMAC hardware peripheral, and the app is calling into the kernel using syscalls to set up this, to tell the kernel to set it up, and then the app's saying run the HMAC and yielding. So while this HMAC is being generated, the app's yielding, it's not running, and any other apps could run. And then we're getting a callback once the HMAC operation is complete. So now we're creating a NIST elliptic curve crypto P256 secret key. We're calculating the public key, and we finished generating both keys, the public and private key. And now we're using that to generate, to attest some data. Like I said, the nonce is all zeros. That's definitely not secure and not a good idea, but that's what it is for now, and finished. So as you can see over here, we correctly authenticated or registered our key. So we're going to save it as the OpenTitan security key. So you can save. So you can see now in my two-step verification, there's just one key, the OpenTitan security key, and it's using web or then. So now I'm going to make sure I reset all my trusted computers, and now I'm going to open up a new window. So this is an incognito window, and here we go. So I'm going to try and log into my account now. So let's log in. Let's go CTAP test, password, login. So now notice this time it wants a two-step verification. So we're going to say use your security key. And when I do this, watch over here on the right-hand side. There we go. So we're regenerating our signing key based on this data that we store. So we store only some of the data in the actual key, and so we regenerate it. The nonce, we stored the nonce, and we finished. And now we logged in to our Fastmail account using two-factor authentication with TOC on OpenTitan as the CTAP example. All right, one thing I forgot to show as well, actually, is if I run a dmessage, you can see this. So this is a little earlier, but this is the product being connected, or the OpenTitan USB device being connected, new USB device found, vendor, ID product, and new USB device settings, product, OpenTitan, TOC OS, manufacturer low risk, and the serial number. So this is just showing that what happens when you actually plug it into your computer once we've loaded this app. So that's it. That's the whole demo. If you have any questions, let me know.